Integration is about adding up tiny pieces to get a total. That's it. That's the core idea. If you've ever added up a bunch of numbers, you already know the basic idea. But integration takes that and pushes it to the limit. Literally. Let's start simple. Imagine you're painting a road. You divide it into 5 equal sections. In each section, the amount of paint you need per meter is different. So for each section, you multiply the paint needed per meter by the length of the section. Then you add it all up. That gives you a rough estimate of the total paint needed. Now, what if the paint needed per meter changes smoothly along the road? Like, it's not constant in each section, it's gradually increasing or decreasing. Then, dividing into 5 sections isn't enough. You divide into 10, then 100, then 1,000. As the number of sections increases and each section gets smaller, your estimate gets better. In the limit, as the width of each section goes to 0, you're no longer doing a sum, you're doing an integral. That's what this symbol means. Integral. It's a fancy S for sum. But it's a continuous sum. You're adding up infinitely many tiny contributions. So when you see something like integral from a to b of f of x dx, here's what it means. F of x is the amount per unit, like paint per meter. Dx is a tiny piece of the domain, like a tiny bit of road. F of x times dx is the tiny amount of paint needed for that tiny bit. And the integral adds up all those tiny amounts from a to b. Now let's make it visual. If you graph f of x, the integral from a to b is the area under the curve. If f of x is positive, the area is positive. If f of x is negative, the area is negative. So the integral gives you the net area. That's why if f of x represents profit per day, the integral gives you net profit, gains minus losses. Let's go physical. Suppose f of t is velocity in meters per second. Then f of t times dt is a tiny displacement, meters. And the integral from time a to time b gives you total displacement. So integration turns a rate into a total, velocity into distance, power into energy, density into mass. And here's the kicker. Integration and differentiation are opposites. If you know the rate of change of something, integration gives you the total change. If you know the total change so far, differentiation gives you the rate. This is the fundamental theorem of calculus. It says that if f of x is the integral from a to x of f of t dt, then the derivative of f is f. In symbols, f prime of x equals f of x. And if g is any antiderivative of f, then the integral from a to b of f of x dx is g of b minus g of a. That's why we compute integrals using antiderivatives. Now, there are 2 kinds of integrals. A definite integral, like integral from a to b, gives a number. It's the total accumulation. An indefinite integral, like integral of f of x dx, gives a function. It's the family of all antiderivatives of f. That's why we add a constant c, because differentiation loses constant information. Let's generalize. Integration is always about multiplying a density by a tiny piece of space and adding them up. Mass is the integral of density times volume. Work is the integral of force times distance. Probability is the integral of probability density times dx. It's always the same structure. Amount per unit times tiny unit equals tiny amount. Add them all up. You can even use integration to find the average value of a function. The average value of f over ab is 1 over b minus a times the integral from a to b of f of x dx. It's like asking if the function were constant, what value would give the same total? So here's the mental model. When you see integral from a to b of f of x dx, think f of x is how much per unit. Dx is a tiny unit, f of x times dx is a tiny amount, and the integral adds up all the tiny amounts from a to b. That's it. That's what integration represents. And this idea extends. In higher dimensions, you integrate over areas or volumes. In physics, you integrate along curves or surfaces. In probability, you integrate over distributions. In advanced math, you integrate over abstract spaces. But it's always the same idea. Total equals sum of tiny contributions. So next time you see an integral, don't just think area under a curve. Think accumulation. Think density times size. Think rate times time. Think adding up infinitely many tiny things to get a total. That's what integration really means.